now. Okay, so now, in fact, what we have learned in the previous lessons, where we're going to where we have derived this Michaelis-Menton's equation. So this Michaelis-Menton equation actually has the limitation. So now let us look at what is the limitation. Okay, what is the limitations? Yeah. Okay. So according to Michaelis and Menton's, the equations that link V naught, V max, substrate concentration, Km. Okay, this equation actually, okay, we need the Vmax and Km value to be determined first, correct? If we don't have Vmax value, we don't have Km value, so whatever substrate concentration or substitute actually useless, right? Okay, Vmax, what is Vmax? Don't know. Km value, don't know. So that's the problem. So we need to determine the Vmax value from the curve. Okay, this curve is known as V naught versus substrate concentrations curve, where we get these, right? Okay, and then yeah, from here we get the Vmax. And then we have a half Vmax. And then we get the Km. So you see that, oh yeah, can right? We can get the Vmax, we can get the Km. But the question here is, when you look at the definitions of Vmax, again, when Vmax occurs, substrate concentration no longer act as limiting factor. Correct. So when substrate concentration no longer act as limiting factor, only we can claim Vmax. So the question here is, how high the substrate concentration? How high the substrate concentrations? Okay, for us to actually define it as, oh, very, very high until my substrate concentration no longer act as limiting factor already. So in fact, if you carry out the experiment, you won't get this kind of graph. You're going to get this graph. This is a theoretical Vmax value. This is a theoretical Vmax value. Vmax actually on paper only. We won't be able to achieve Vmax for every single reaction. We won't be able to achieve Vmax because no matter how you do it, you will be approaching and keep on increasing. You won't get the Vmax actually. Are you clear? Vmax is just a theoretical value. So if you can't determine the Vmax from the graph, can I use this equation? I can't use this equation at all. So that is a limitation of this equation, because if you can't find the correct Vmax, the true Vmax, then you won't get Km. Correct or not? If you don't know what is the Vmax, because this is the theoretical value. Are you clear? So you're only approaching, but you can't actually get that particular Vmax. So therefore, okay, therefore this equation has a limitations. Are you clear? Okay, so if you can't get the true Vmax, you won't be able to get Km as well. You won't be able to have the Vmax, right? So means that this equation a little bit useless now. I say that. Are you clear? Okay, I don't say it totally, but if you can't get Vmax, you can't get Km. Therefore, this equation actually we can't use it. Okay, and one of the thing here is, if you achieve Vmax according to this reactions, then we know that to achieve this, substrate concentration must be very high, and it's impossible for us to do it in the lab, right? How high is high? Okay, so the only things that we know that when the substrate concentration approaching infinity, are you clear? That is very high. So how rich is rich? We always say that 1 billionaire or billionaire or trillionaire. Can I see that? Unless infinity, then that is very, very high, and which we won't be able to do in the lab for us to actually determine the Vmax. Are you clear? So Lineweaver-Burk actually modified this equation, become a double reciprocal equation. So what's mean the double reciprocal equation? So basically, we use this equation, use back this equation, and we put 1 over to these equations. So therefore, what we're going to get here is 1 over V naught equal to Km. plus substrate concentrations over Vmax substrate concentration. Okay, clear or not? You invert it, inverts the equations. Are you clear? We invert the equations now. So in order to get this double reciprocal plot, or okay, the name, I mean, in our syllabus we call it double reciprocal plot, or in another name for this plot also termed as the Lineweaver-Burk equation. So we get the double reciprocal, so it means that 1 over V naught will equal to Km plus substrate concentrations divided by Vmax substrate concentration. Okay, so you learn about this, right? Linearize the equation in your physics. Okay, so 1 over V naught now equal to Km over the Vmax. Okay, I put it this way. Okay, Km over Vmax multiplied with 1 over substrate concentration plus substrate concentrations divided by Vmax substrate concentration, correct? Not maths. Okay, so not sure, ask your maths lecturer. Okay, so what actually happened here is, can you see that substrate concentration I can cancel here. So now my equation now is 1 over V naught equal to Km over Vmax. Okay, multiply with what? Multiply with 1 over substrate concentration plus 1 over Vmax. Those who take at maths, you know this equation already. Why? Because this is Y equal to mx plus c. So this is Y, this is m gradient, this is x axis parameter, this is c, means that Y intercept. So means that if I plot a graph now, if I plot a graph, instead of V naught versus substrate concentration, now I plot 1 over V naught versus 1 over substrate concentration. Can you see that double reciprocal? I will get a straight line. I will get a straight line. If I plot this graph, I'll get a straight line. And if I extrapolate this straight line, it's going to cut my x-axis and y-axis now. Are you clear? Vertical axis and horizontal axis. So this is the y-intercept, correct or not? Or what I call this vertical axis intercept. So means that this value actually equal to 1 over Vmax. Can you see that? Are you clear? This value will equal to 1 over Vmax. And if you use the gradients, okay, if you use the gradients, then this value you can calculate later, it gets negative 1 over Km. So from this double reciprocal plot, I can get these two values, Vmax and Km, and then I can substitute back to the original equations, okay, or my Michaelis-Menten equation to get my V naught from the substrate concentration values. Are you clear? Okay, so again, if you look at this part here, okay, y equal to mx plus c is the equation of a straight line. So it means that if I plot the graph 1 over V naught versus 1 over substrate concentration, then the y-intercept here is 1 over Vmax. So it means that this is the value of 1 over Vmax. Okay, so how I get this? How I get this value? Y is negative 1 over Km. So now we learn about this in mathematics, right? Gradient equal to negative y-intercept divided by x-axis intercept, right? You learn about this in your mathematics, correct? Okay, gradients equal to negative y-intercept over x-intercept. So gradient is what? According to the formula here, gradient is Km over Vmax. Okay, so gradient is Km over Vmax. Negative. Okay, y-intercept. Y-intercept we have already 1 over Vmax. So what is my x-intercept? So you bring it, so x-intercept will equal to negative 1 over Vmax divided by the Km over Vmax, correct or not? And also equal to negative 1 over Vmax multiplied with Vmax over Km. So Vmax cancel, so negative 1 over Km. Okay, so means that now I have this value, therefore I will be able to determines the Vmax and Km. So how I determine Vmax and Km? Now, for example, here, if this is a graph, if I plot 1 over V naught, this is the ones that 1 over substrate concentration. If I have graph, so if this is the value equal to 0.5, for example, this value, let's say negative 2.0, for example. So how I get Vmax value? Okay, so I know that from this graph, 1 over Vmax equal to 0.5. Are you clear? If the 1 over Vmax equal to 0.5, therefore Vmax will equal to 1 over 0.5, answer equal to 2. Okay, then it depends on what is the units here. Okay, so how we calculate Km? So we do know that negative 1 over Km equal to negative 2.0. So means that negative we can cancel, Km will equal to 1 over 2. Are you clear? So it depends on the unit. Okay. Can you see that? So what is a unit? So units here actually is mole per means the rate of reaction is mole per second. Okay, how many mole of product form per second? Are you clear? Okay. So this is how we get the value. You can copy down. So first part, how I derive it. Okay, now why we need to do this? Why we need to do double reciprocal plots? Because it is impossible to obtain Vmax, okay, from Michaelis-Menton's plots. Okay, for the graph, the Michaelis-Menton plots, they're impossible for us to obtain Vmax. So means that, so impossible for us to know Km also, impossible. Okay, so therefore we're going to reciprocate our graph. So that's why we need to plot the double reciprocal plot. Okay, we need this double reciprocal plot. So this double reciprocal plot, actually how we do it, you need to know what we plot. So we plot 1 over V naught versus 1 over substrate concentration. Do I need to remember the formula? The answer is no need. Okay, no need for us to remember the formula, but you need to know what we plot. We plot 1 over V naught versus 1 over substrate concentration. Okay, so you will again get a straight line. You plot this, you're going to get a straight line. So this is the example. Okay, you plot 1 over V naught versus 1 over substrate concentration. Can you see that? You double reciprocate both S's already, then you get a straight line. So this straight line actually will cut at my y-axis or vertical axis and horizontal axis, and we need to know what actually represented by these two value. So at y-axis or 1 over V naught axis, this one actually is 1 over Vmax. Okay, this part actually is negative 1 over Km. So from here, you will be able to get the Vmax value and Km value. Then only we will be able to actually get the we will be able to get the Vmax and Km value to substitute into the Michaelis-Menten equations Therefore, we will be able to predict the V naught value from the given substrate concentrations. Are you clear? Okay, so these are the things that we need to know for our syllabus. Okay, so you can actually take a snapshots here. Okay, so now let's look at this Lineweaver-Burk equations, also known as a double reciprocal plot. Double reciprocal plots. Okay, so this equation actually modifies this Maclaurin-Menten equations. Okay, so how we do it? Okay, as I say that Vmax is approached asymptotically, and it's impossible to obtain the definitive value or true value from a typical Maclaurin-Menten plot. And if let's say we can't get the Vmax, then Km also cannot be determined. Are you clear? So what this double reciprocal equation can be obtained by taking reciprocal of both sides of Maclaurin-Menten equation, then you will get this formula. Okay, this equation. So the question here is, do I need to remember? No, no need to remember these equations. Okay, so I have done the derivations of the Lineweaver-Burk equations, so you can actually copy it in here, or you can take a snapshot and then paste it. Okay. So a double reciprocal Lineweaver-Burk plot of enzyme kinetics is generated by plotting inverse initial rate of reaction 1 V naught versus 1 over substrate concentration. So gradient not so important, but these two you need to know. Okay, the intercept of the vertical axis is 1 over Vmax, and intercept of the horizontal axis is negative 1 over Km. So this we need to know. Okay, so now we look at the applications. Okay, so how we do this? Very simple, guys. So when come to the practical, you always have the substrate concentration. Here, can I see a substrate concentration? So in this case, in molar. Okay, molar. So you determine, right, substrate concentration 0.02. What is the initial rate of reactions? And you determine, so increase. Can I see that? You increase the substrate concentration, you determine the V naught. Okay, so what we can do here in this part, for group 2930, you can continue to plot the graph, because I have taught you guys how to plot the graph already, okay, in the previous lesson. So we can plot this graph. For group 4, you may not be able to plot the graph yet, because I haven't shown you guys how to plot the graph yet according to the CIA Cambridge standards. I will teach you guys tomorrow lesson, okay, 3 to 5 o'clock. Those I'm going to talk about this, okay? So what you can do now, later, you can plot the graph and you realize that we won't get the Vmax. Can you see that? Continue to increase. You won't get the Vmax yet. Can you see that? You won't get the Vmax yet. Are you clear? Okay. See? So therefore, in order to get this Vmax and also the Km, I need to reciprocate each value. So 0.02 become 1 over 0.02, 1 over 0.04, and so on. V naught also 1 over, I will get this. Then I can plot this double reciprocal plot. So from this double reciprocal plot, then you can determine the value of Vmax and Km. Is a practice for you guys. Okay, so you guys can try do this. Okay. So what I want to do here is try. Okay, let you guys try this. What is meant by this? Okay, how we apply this Lineweaver-Burk plot for competitive and non-competitive inhibitions. Okay, so I give you the graph now. It's without inhibitors. Now you have to think how to plot for if these reactions. Now I add in small concentrations or low concentrations of the competitive or non-competitive inhibitors. Okay. Okay, so let us look at the effect of the competitive inhibitor and non-competitive inhibitor onto these double reciprocal plots. Okay, so a quick revisions here. Okay, so competitive inhibitor, we know that Vmax remain the same, right? Okay, I put equal means the same lah, and then Km actually increase. Okay, why increase? Because affinity decrease. Okay, the Km value increase. Okay, so next. For non-competitive, If non-competitive, then you can see that, okay, these are Vmax now lower. Okay, Km remain the same. Okay, no change. Okay, so this is what we have learned previously. Okay, so now we look at how this thing, this inhibitor, competitive inhibitor, non-competitive inhibitor actually affect the double reciprocal plots. Okay, so again, let us draw this one. This 1 over V naught. This is 1 over substrate concentrations, and we do have one line already. Okay, so this is without inhibitor. Okay, so and we do know that, okay, these two particular point is very important because one represent 1 over Vmax here, and this is 1 negative 1 over Km. Okay, so now look at this. We start with this simple, first thing, competitive inhibitor. So because competitive inhibitor, Vmax remain the same. So it means that 1 over Vmax still remain the same. So it will be here. Okay, I use blue color. Now, how about Km? Now look at this. If Km increase, correct or not? Then negative 1 over Km also will be higher. Am I right? Can you get my the things? Now look at this. So if you're not sure, you can try this. So Km value, negative 1 over Km. If original Km value is equal to 1, okay, so here will be negative 1 over 1. So equal to negative 1. Are you clear? Can I see that? But now Km increased to 2. If Km increased to 2, means that it will be negative 1 over 2, correct or not? So equal negative 0.5. Which one is higher? Negative 0.5 is still higher than negative 1, right? If I actually, okay, try to imagine that I owe people money, I owe bank 0.5 million, I still richer than those owe the bank 1 million, right? Cannot. So negative 0.5 is still higher. So it means that the new negative 1 of Km will be here. So the graph will be this. Oops. Let me undo a bit. It's very difficult for me to draw. Yeah. Okay, you draw. Okay, so this one is with competitive inhibitor. Okay, the blue lines. So we have the new negative 1 over Km, but Vmax remain the same. So this is the original. Okay, the red color is for the no inhibitor. Okay, so now look at this. For non-competitive inhibitor, relatively easy because Km remain the same. I use the green color, so it means that negative 1 of Km won't change. Correct or not? Okay, but now Vmax decrease. When Vmax decrease, 1 over Vmax, you try to imagine Vmax decrease, 1 over Vmax actually increase. Correct or not? So higher, 1 over Vmax will be higher. So draw. Okay, whether parallel or not, it doesn't matter. Okay, whether parallel or not, doesn't matter. So this is the new 1 over Vmax for the green color, and right here. So this line is for the non-competitive inhibitor. Okay, so the line, they may or may not be parallel, doesn't matter, but you can see that, okay, Vmax, 1 over Vmax will be higher for the non-competitive inhibitor, okay, and negative 1 over Km will be higher for the competitive inhibitors, okay. So you can copy down this one into your notes.